Oh, okay. Hang on. Uh, okay. So today, I'm going to be talking to you about, I guess, about two different papers that I was a part of, and they both involve, well, taken as a whole, they involve, as stated here, comparing the different properties of past and future SARS-CoV-2 variants. And you'll see what exactly in just a second. So, just some background, as I'm sure all of you know. Starting in autumn 2020, then new variants of SARS-CoV-2 started emerging. So first there was alpha, right? Beta, gamma. Well, I mean beta and gamma, kind of came and went, right? But then delta, like alpha and delta were the two big ones. And then after that, of course, Omicron, is the really big one. And because each one of these variants carries with it genetic mutations, right, compared to the wild type, that's what makes it a variant. Uh, well, these mutations, on the viral proteins cause them to be better or worse at spreading, and also more or less severe effects, such as severe illness or mortality from the variant. And this is obviously very important to discover the I guess the properties of these. Like if you for instance, if you have something like Omicron, for instance, where at the very start of the Omicron wave, then people were talking about, like, oh well, it seems to be milder. Well, how do can you measure that? How do you measure that? And furthermore, in the second half of this talk, then because new variants were emerging all the time at that point, then it was also kind of an open question of how do they emerge? Like what can cause a new variant to emerge, and how can we avoid that? So that's kind of what I'm going over in this talk. It's all about variants, pretty much. Um, and so, in order to find out the transmissibility and mortality rates, the two really big ones, as well as R naught, which a lot of epidemiologists really care about. But in order to find out those properties of different variants, then for each variant that we tracked, or each lineage that we tracked rather, because we also did this for wild type. Then we constructed an SIR style ODE system with a bunch of different compartments, as you'll see on the right hand side of the slide. And so in here, then you've got susceptible, vaccinated, actually two components for that, because we investigated the effects of booster doses. So we've got full vaccination, which is the completion of the original series, and acquiring a booster dose, which is one or more doses on top of a full series. Then we've got the different categories which follow from being exposed to the virus. So exposed, asymptomatic, and infectious, right? In Because as we all know, a significant portion of COVID infections are asymptomatic. And then we've got recovered, and then dead of the disease. Uh, so we assume that vaccines give partial immunity, and we also assume that transmission is possible in these asymptomatic and exposed stages, because that is what was seen in real life. Uh, However, as you can see from I guess this giant fraction with n as the denominator here, governing the movement out of the susceptible component, then we've got here these scaling constants theta and delta that represent the reduction in transmission, that is associated with being in the exposed or asymptomatic states rather than being infectious. Uh, Everything else is a fairly standard SIR model, but I guess the fun thing that we did, well, one of the fun things we did here, is in order to fit some of these parameters, well, if you notice here, we've got like a lot of these parameters may be time dependent. So for instance, beta, right? We've got denoted here as beta of T, right? Beta is the the infection, the rate of infection. That varies over time, right? So we know that because there may be different things like lockdowns in place, or people adhering more or less to social distancing or various other things they might do. But the transmission rate varies over time, and so do a lot of other things. And so transmission, vaccination, and death, we took to be cubic spline functions. And for the transmission and death rates, then we used an inverse method, I guess that was first constructed by my supervisor, Professor Wang. And we used some data on confirmed cases and confirmed deaths in three different countries, actually, uh, because we calculated the properties of these variants for three countries. Those would be the U.S., Canada, and South Africa. And so for mu, the death rate, you can see this down here as being sort of the end result of this inverse method. But as you can see, I guess we start with the numbers of confirmed cases and confirmed deaths, and we go back into our model, and we assume that the number of confirmed cases and confirmed deaths are just the movement into I guess the different the different categories that you can see here. So the dead category and the infected category, because the infected category is the one that people actually detect, right? So from there, then we derive the I guess various intermediaries, such as the number of exposed individuals over time, and then the number of infected individuals over time from that. And so we eventually get from this inverse method, then we get the time varying death rate. And so for all parameters, I guess for the sorry, I haven't eaten anything today. So for the parameters, for other parameters, then we fitted them using Markov chain Monte Carlo. And these are like I said, the uh the rates of people at which people receive vaccines, so either completing a full series or receiving a booster dose, then we said those are time varying as well, right? Uh, and we also have data on that. So we used our data, which was also from these countries, because back in those days of the pandemic, everyone tracked all these things, right? And so we assumed that we use Markov chain Monte Carlo to get the vaccination and booster dose rates, as you can see here on the right hand side of the slide. I guess in the third bracket down here are just our objective functions. If we had I guess the number of people who've ever been vaccinated and ever received a booster, because those are tracked. We had those actually those are thanks to our world in data. So thank you to those guys. So we just compared I guess the predicted versus actual, and then I guess for each potential set of parameters denoted theta hat, uh, and then we just picked whichever one was the best. 'Cause that's how it works. So for the effective reproduction number, we also calculated this. So this is sort of like R naught in practice rather than theory, because R naught is basically just at what happens at the very start of an outbreak, right? like when everything's first taking off. So no restrictions are in place. Everything like infection is just kind of happening willy-nilly. There aren't really any constraints on who can get infected. Uh, with who is already infected or anything like that. But the effective reproduction number is just a generalization of this, which is the total number of infected people generated by an infected person at any stage in the outbreak. And so as you can see, this depends on I guess the numbers of well, first of all, the number of potential infectees, right? That's what you've got on the left hand or on the right hand side of the equation, but the left hand side of the right hand side. So if you've got the susceptible people plus the amount of the scaled down proportions of people that have been fully vaccinated and that have received a booster, because we assume partial immunity, right? So if we've got this potential pool of, people who could theoretically be infected, and then on the within these parentheses here, then what you've got instead, so what you've got over there is the total number of cases generated. So you've got infections by like it because you'll notice here you've got theta 1 minus rho and then times nothing and then rho times delta, and you might remember those look eerily similar to stuff you saw over here, where if you look at the movement out of the susceptible category, then you'll remember the scaling constant for the decrease in infectivity from exposed relative to the baseline of infected people is theta, and this the corresponding constant for asymptomatic people is delta, and of course we've got rho is the proportion at which exposed people proceed to being asymptomatically infected rather than symptomatically infected. So that's where all those come from. You can see that here. And so we use this to generate the effective reproduction number over the entire course of the outbreak, or all the time we tracked at least, for all the variants we tracked, right? Once again, this was the wild type, and then Delta and Omicron. And so what did we find after doing all this method? So like I said, we fitted the model to data for 3 different countries. South Africa, which is what you see here. All this, all these graphs that you see on the right hand side of the slide here. These all represent the scenario in South Africa. We also did for the U.S. and Canada, but just so I don't have a ton of figures to show you, then those are not on this slide. But if you do want to look at them, then they're in the paper that came out of this, which is really good, and you should have a look at it anyway. So what are we looking at here? So in the left-hand column, then we can see I guess the cases and the transmission rate, whereas in the right-hand column, we can see the deaths and the mortality rate. And note also the difference in axes, especially when it comes to Omicron. Because if you look at the transmission rate for Omicron, then it was significantly higher than the other variants, as you can see from the really cool cubic spines that we added. But the death rate, as you can see, is on the order of 10 to the minus 3 for Omicron. And that's much lower. That's an order of magnitude lower than what we saw for Delta and what we call the other variants, which is basically everything other than Omicron and Delta. In other words, basically the wild type. And so you can see here, that's confirmation directly from the data, that the Omicron variant was in fact much more easily spread, but at the same time much less lethal. Uh, and so for the effective reproduction number, same thing generally. Like if you look at the Omicron variant compared to the other ones, so here I'm showing you everything from all three countries. South Africa in the top row, US in the middle row, Canada in the bottom row. And if you look at it, then the effective reproduction number for the Omicron variant, like especially Omicron being the rightmost column, then if you look at it, especially at the peaks, right, then it reaches levels that the other variants just don't reach ever. Like you don't see them ever getting up to effective reproduction numbers of close to 10, for instance. Which is that's very high. Like everyone was talking about like at the beginning of the Omicron outbreak how the R naught for Omicron was ridiculous, and here's confirmation that it was over the entire course of the outbreak. We have also marked with this green line here, the effective reproduction of number of one. But I guess if you're in this meeting, you probably already know what that means. But for those, just for the benefit of everyone, then above it means the disease spreads. Below it means it dies out. Uh, and so another thing we did was because we had all this data on vaccination, right? So we decided to look at how many cases were prevented by vaccination. And it turns out the answer was a lot. And so we did this for the US and Canada because in South Africa we didn't have reliable data for it. But So because Omicron was able to I mean we knew, right? Omicron was able to kind of get around the original vaccines, but a booster dose wasn't that bad in terms of like you could get decent protection if you just got a booster dose from one of the vaccines geared towards the wild type. Like it protected you against Omicron reasonably well. And reasonably well, in fact, was enough for preventing, according to our calculations, about 40 million infections in the U.S. and about 1 million in Canada. You can see here in the right-hand column of these graphs what the uh, well in the left-hand column then you can see I guess the infections with and without the vaccines. And of course we can simulate that, right? Because we can just assume that the time varying vaccination rate, which I showed you uh all the way back here, uh we can just assume that's zero, right? So on the left-hand side of these graphs, left column, then you can see the infections with and without vaccination. And on the right-hand column, then you can see deaths, and it looks like we did in fact prevent quite a lot of deaths by the vaccination and booster dose administration. Uh, and so also one additional thing that I didn't get into in this presentation before I get into this next section is that what we also did here is we actually compared I guess the properties of these variants additionally with influenza, both the seasonal influenza, like the strains that just kind of pop up every winter in Canada and the US, and also the really big like H1N1 variant that was really big back I think about like a decade and a half ago now. But that so that was actually a very good point of reference because we did actually find out that Omicron was like in terms of its infectivity and its mortality, then Omicron was actually more similar to influenza than it was to the other COVID variants. So that's pretty big, but it didn't fit with the I guess what else I had in my presentation because I guess I'm talking about variants here. because I wanted to incorporate the other paper as well. But if you want to look at those results, they're really big and they're pretty cool. So I advise you to go look at that paper. But anyway, so back to variants here. So I talked here about how Omicron was able to be significantly mitigated based on vaccination. And so you might think, okay, well, if we manage to reduce the spread of Omicron and reduce the number of deaths due to Omicron by vaccination, could vaccination also help mitigate future strains? And so here we actually drew upon the framework of coupled human and biological dynamics. And so what we did here was we actually incorporated vaccine uptake directly into an SIR model in the sense that we actually had a component for how willing people are to receive vaccines, because that allowed us to answer questions about like when if a significant number of people are not willing to uptake vaccines, then how bad does this make everything? Uh, and So we actually constructed two models. We had a deterministic model and a semi-stochastic model. And these featured two strains and the social dynamics that I just mentioned. The semi-stochastic model we used to find out stuff about the actual emergence of these variants. So treating the emergence of a new variant or mutant lineage as a stochastic event, and then we used a deterministic model once it had already emerged. Uh, so for the semi-stochastic model, then we did simulations for related to how likely it was for a new variant to emerge. We ran it many times. So we'd run it 100 times under different conditions, and we'd find out how likely out of those 100 times, how many does the new variant emerge in, right? But then after it does, then we would switch to the deterministic one, and then we'd calculate stuff like how many people get infected and how many people die or mostly infected, right? Mostly how many people get infected over the course of the outbreak. And these two models, semi-stochastic and deterministic, were, essentially the same in the sense that all their components were the same, and movement between the components was governed by the same rates in each one. Uh, so the deterministic model, which I'll introduce first because it's mathematically less complex, was like the one previously mentioned. So if you remember that one, similar because just because it's an SIR model, but because we've got two strains that we're dealing with, and people could get infected by either strain. Because remember, this is after the new one came out, right? So you've got E1 and E2, A1 and A2, I1 and I2, right? Uh, because you can get exposed, asymptomatically infected or symptomatically infected by strain one or strain two, right? But of course, if you're susceptible, vaccinated, recovered, or dead, then I guess it doesn't really matter. And then you've got this thing down here, X. So what is X? X is what I told you about before. What X is the proportion of people that are willing to take a vaccine. And so so this used replicator dynamics. So these were pioneered by my PhD supervisor, a guy by the name of Chris Bao at the University of Waterloo. And so he's done a lot of work on these. And so what the replicator dynamics do is they combine so I guess social imitation. So you want to be like your neighbors, with some sort of intrinsic payoff function, which is like, does being vaccinated or not being vaccinated convey more benefit in a general sense. And So for the differential equation, dx dt, then the parts of it, kx times 1 minus x, that's the social limitation part. That's the part where like if there are a lot of people and they're all vaccinated, and you want to be like them, right? Because you want to be like your neighbors, then it goes towards a steady state at 1, right? But if for 1 minus x, if you or I guess yeah, x, yeah, 1 minus x, right? But also you've got, because you've got both x and 1 minus x, you've got steady states at 0 and 1, and you get pulled towards one of those two, uh, depending on uh, depending on if everyone around you is vaccinated or everyone around you is unvaccinated. Uh, and the strength at which you move towards these equilibria is greater if I guess the more homogeneous the people around you are. Because if you'll notice this, right, then the also the this parameter k here is that's just the scaling rate, just to make sure, just basically just to make sure, like, to scale everything according to how fast the people switch between compartments, vaccinated, willing to become vaccinated or not willing to become vaccinated. And then this delta F, that's the payoff function, right? So if delta F is positive, then that means right now, it is more beneficial to get vaccinated or to want to become vaccinated. And if delta F is negative, then it is more beneficial to not be vaccinated. And so what we assume for delta F, which was kind of an oversight for not including this in this explanation. But what is in delta F, is we assume that getting vaccinated incurs a small penalty, because I guess when you do, then there is some chance you get like mildly ill for a day or so, and and then that's the end of it. You're pretty well protected after that. And then but Also, not being vaccinated has a penalty that varies based on how many cases there actually are, because just generally your likelihood of being infected and dying, because obviously that's something that people worry about. So if there are a lot of people, and you're very likely to get infected, then it is, then the harm coming, the harm that you receive from not being vaccinated would be, pretty substantial. On the other hand, if the number of infections right now is 0, then there's kind of no point. So the harm gained from not being vaccinated is pretty minimal. Uh, so Now I'll mention the semi-stochastic model. So how the semi-stochastic model works is that you so each of these components in the I guess in the deterministic model is also a component in the semi-stochastic model. So we start with a fixed population, and these people in the population can move between components. And so what happens is, so we simulate, like, we just advance the model. We advance the model by, I guess, by incrementing time, and at each time step, what we do is we assume that one rate in the model has happened, and in order to find out which one it is, then we have these propensity functions. So as you can see in the rightmost column, then you got the probability for, like, if we advance time by some small amount dt, right? Then this then the what you have here in the rightmost column is the probability that the I guess the rate that corresponds to which row it's in is the one that happens. And so for instance, one of the things that can happen in our model is people that are susceptible becoming exposed to viral strain number one, right? And so the rate that that can happen in the deterministic model is, beta one, theta one, E1, S over N, which is exactly what you can see. Well, it's what you can see here, but we folded a lot of these constants into I guess into other constants such as lambda, the lambda constants for readability here. But if we've got this rate, right, then the probability of that being the event that happens, someone that is susceptible becoming infected by viral strain one, the probability of that being the thing that happens is basically just that. It's basically just that rate, except scaled according to how much time we incremented by, the reason for that being that like obviously if we increment time by like a second, then it's not very likely that that a whole lot of things are going to happen during that time. uh so that's mathematically how this works. So it's a semi-stochastic simulation, because the stochasticity is in choosing the stuff that happens over time. And so what we did is, in order to find out if vaccine hesitancy can cause a variant to emerge, then we varied RV, which is the like it's folded into the delta F, which is makes it a real oversight that I didn't include in this presentation. But I guess one cannot think of everything. But so that is so RV is I guess the perceived risk of vaccination. If it's higher, then that means that fewer people are willing to become vaccinated. Yeah, it's included as part of the penalty term for being vaccinated in that in the delta F, the XDT that you saw back there. But it turns out increasing that actually really does something. Like it does a substantial thing. And so what it ends up doing is increasing the perceived risk of vaccination ends up causing the rate at which new variants emerge, or the probability that new variant will emerge by a factor of four. Over the course of the 300-day window that we simulated for. What you can see here is I guess like, because we're doing this with stochastic simulations, right? So each so in these graphs, hang on. So in these graphs, each one of these kind of lighter gray traces corresponds to the I guess one run of the semi-stochastic model. And so on the top, then you got the daily number of new wild type cases. I mean, the wild type always exists. So there's no emergence there. It just always exists. And then middle row, you've got daily number of new cases from the mutant lineage. Lineage number two, the one that could, that doesn't exist at the beginning but could emerge, because of the I guess over here, then you've got, direct transmission between, you know, S, I guess susceptible and exposed to number two. Uh, but you've, uh, but you've also got, like in here, you've also got, there's a viral mutation rate, which I should have mentioned before. But if you'll notice here, back in this, back in the model that I construct or that was constructed, then you've got this thing U, right? So what is U? U is basically a viral mutation. So if you're infected, if strain one spreads to you, then there's a probability of that it mutates into strain number two, the mutant type, and you're infected by the mutant type instead. And probability one minus U that that it just, it stays what it is, or I guess it requires some mutation, but it's, the mutation isn't enough to turn it into a new lineage. But we kept U very small, right? Because obviously this is not something that just happens willy-nilly. Right, that's how the mutant strain can emerge. But So if the perceived risk of infection, because that's something else that like really governs like how willing people are to get a vaccine. Because if there's no perceived risk of infection, then nobody's going to do it. But if we if we vary that, right, then that actually had an even larger effect than varying the perceived risk of vaccination. So I guess that's so perceived. I mean, they're both pretty important. But this one, like perceived risk of vaccination, is associated with a fourfold increase in probability of a mutant strain emerging. I guess altering the perceived risk of infection gave us I guess even more drastic changes. So if the perceived risk of infection is very low, as you can see on the I guess on the left column of these graphs, same as before. Top row is daily number of new cases for the wild type. Middle row is daily number of new cases for the mutant type, and bottom row is the probability that the mutant type emerged in a given simulation. And so you see here, our simulations gave that 50-50 shot over the 300-day time window we simulated over. But if you increase the perceived risk of infection, all the way up to the maximum values that we tested, then it's way lower. It's under 10%. Uh, and so after emergence of this, I guess of the new strain, then what we did is we tested the properties of the like we tested like what happens during a given outbreak as a function of various model parameters such as the mutation rate. I told you guys that was low. Well, here's how low we kept it. You know, on the order of potential, like the baseline values for U were 10 to the minus 6. And so it's not something that happens every day. But so what we found, so one actual interesting result was we actually found that the severity of an outbreak wave, measured in terms of number of cases of a new variant, actually really depends on fear of the previous variant rather than fear of the new one. And you can actually see this with these two sets of graphs right here. Uh, so so what you've got here in this set of graphs is on the vertical axes of these is the fear of being infected by the wild type, strain number one. So RA1 and RI1, fear of being asymptomatically and symptomatically infected by the wild type. And you can see here, for I guess for sufficiently for sufficiently low mutation rates, then and actually for most mutation rates really, then you do get quite a bit of dependence on this. But however, perceived risk of being infected by the mutant strain doesn't really seem to do anything. So plotting that against mutation probability, stuff like the peak number of infections, so maximum caseload per day, the time at which the maximum caseload happens during the simulation, and how many infected there were, at the very end of the simulation, for both wild type and mutant type, wild type being the top row, mutant type being the bottom row. Then there's like no dependence on the fear of the new strain. It's all about how it is basically all about like how scared people were about the existing strain when the new strain emerged. I guess, how to interpret that in real life. It would be something like if people are sort of like lulled into complacency and they don't really do anything, then if a new variant emerges, then they're just going to think like, okay, whatever. And I guess they're not going to really take preventative action. Whereas if people are super vigilant about variants, and they're really scared of COVID or whatever disease we're modeling, because this model is very generalizable, then obviously if the new variant comes, then they're gonna really care about it, right? However, because this new variant, right, like I mean, people really only start worrying about it after they know about it. And the initial stages, when the infections are, when R naught is the highest, when people are getting infected the most, then it's sort of still in that initial stage where maybe not everybody knows about it, or I guess people still, are kind of figuring out like, what to do about it. And so by the time people are, kind of up in arms about this new disease happening, then, a lot of people have already been infected. So that's kind of the takeaway from that. Um, but what happens if a variant does emerge? So we also tested like how to potentially control a new variant if it does. And we had two different ways of doing this. So a rapid vaccination campaign. So just like increasing, rapidly increasing the number, the number of people who are vaccinated, and also non-pharmaceutical interventions. So artificially reducing the transmission rate. So these had orthogonal effects, right? Because they affected different parts of the model, and therefore they complemented each other very well. So if you do both, then it turns out that is what minimizes the caseload. Uh, so uh, so as you can see, like this is similar to these graphs that I showed you back here. This is for I guess just plotting in each column the fear of infection of the wild type, because that was the parameter that we found did the that that was the parameter that we found had the greatest effect. But it turns out that if you do both of these at the same time, then compared to these scenarios over here, like especially in cases where people aren't really that scared, then if you implement both of these at the same time, it does produce a much lower chance of producing this mutant strain. Uh, right. If you do rapid vaccination campaigns and non-pharmaceutical interventions during a current outbreak wave, then it makes it significantly less likely that there will be another outbreak wave for a new strain. So that's what we're getting at here. And so now I'd just like to just very briefly talk about foodborne diseases, even though they have no bearing on this presentation whatsoever. They're completely unrelated to COVID, but it's what I'm working on right now. I just wanted to show you guys that I've actually been doing stuff recently. So I'm working on two projects right now. One of them involves mechanistically modeling norovirus transmission. Everything's redacted because this, since this hasn't gotten published yet, and I guess I'm just keeping it under wraps until it gets published. But I guess here's the model, or the variable names for the model rather. And The other project that I'm working on about foodborne diseases is a data-driven analysis on what drives norovirus and salmonella outbreaks. So, this has this is with data that I got from the CDC, the U.S. CDC, and that with I guess with a bunch of other factors in the outbreak locations of norovirus or salmonella. But once again, I can't tell you what those are until this work gets published. So at the moment, it's just kind of a secret. Uh, so I would like to acknowledge the Fields Institute for funding this work, and the University of Alberta for funding me in general. Additionally, I would like to acknowledge our collaborators at Harbin Engineering University who helped with both these manuscripts, and also to my PhD supervisor, Chris Bao, for suggesting a couple ideas. So Chris Bao does a lot of work on the uh, on this stuff, right? The coupled human and biological systems, and also quite a lot of work on mathematical epidemiology. So cite his papers because he's a really cool guy. And that is the end of my presentation.